In many of the systems associated with the operation of the aircraft and its engines, liquids and gases are used, the pressures of which must be measured and indicated. The gauges and indicating systems fall into two categories: direct reading and remote indicating. A remote indicating system uses a remotely positioned sensing element, which is connected to the pressure source. The sensing element translates the actual pressure reading into an electrical signal. The sensing element then sends the signal via electrical wiring from its remote position to an instrument in the cockpit. A direct reading pressure instrument is physically connected to the source of the pressure that it's sensing. For instance, a direct reading engine oil pressure gauge will be connected via an oil pressure pipeline directly to the engine, to the point where the oil pressure is to be measured. Colored arcs of green, amber, or red are used to indicate the range and limits of the pressure system. Vibration monitoring equipment is fitted to almost all commercial jet engine aircraft. Although gas turbine engines have an extremely low vibration level, any change in that level is usually indicative of damage which may lead to failure. Warnings will be given in the cockpit if the vibration levels are exceeded, and some systems have a continuous readout of vibration levels. Modern engines have the facility whereby the vibration level of each rotating assembly can be monitored, so that the source of any vibration can be pinpointed. The principle upon which vibration monitoring equipment works requires an input from a detector, which can be either a piezoelectrical crystal mounted strategically on the engine, or a fixed coil carrying 115 volts at 400 Hz, the output of which will be affected by the movement of a magnet within it, which is mounted on springs. In either case, the frequency of the incoming vibrations will be amplified, and then filtered so that only those frequencies that are indicative of damage occurring to the engine will affect the output. The output of the detector will affect the current flowing through the coil into the amplifier and filter. The filter will erase any output which is normal to the engine, but allow through to the amplifier any frequency that's considered to be harmful to the engine. The result of this amplification is sent to the instrument via the rectifier and warning circuit. The needle will show the appropriate deflection for the amount of vibration being suffered by the engine at that time. If the level of vibration exceeds a predetermined amount, a warning light on the instrument illuminates. Vibration is measured and displayed in relative amplitude. There are two methods of indicating the quantity of fuel carried in an aircraft. Either the volume, for example gallons, or the mass, kilograms or pounds, are measured. Because the mass of the fuel on board is of more interest to the pilot of a large aircraft than is the volume of the fuel on board, measurement of the volume of fuel is now only used on light aircraft. The simplest form of volume indication is a float system. Early aircraft used a float which sat on the surface of the fuel in the tank. Attached to the float was a piece of wire that protruded out of the top of the fuel tank. As the fuel level reduced, so the wire disappeared from view. A later system used the float to reposition a wiper on a variable resistor. This varied the current flowing to an indicator which had a pointer that moved over a scale calibrated in volume. The system was powered by direct current. The disadvantage of the float system is that the indication is not linear, and there is no provision for making adjustments for system accuracy. The gauge is set to be accurate at the low and empty positions. The system is also subject to errors caused by temperature changes, aircraft attitude changes, and aircraft acceleration. In its basic form, a capacitance system, which is much more accurate than the float system, consists of a tank unit, which is effectively a variable capacitor, located in the fuel tank, together with an amplifier and an indicator. A tank unit consists of two concentric aluminium alloyed tubes, which are held apart by pairs of insulating pins. The coaxial electrical connections are insulated and the unit is insulated from the tank. The principle of operation of the capacitance system is based on the use of fuel and air as the dielectric between parallel plate capacitors, which have a fixed area and a fixed distance between them. The only variable in the system is then the ratio of the dielectrics used, which are fuel and air. That ratio is determined by the quantity of fuel in the tank. Incorporated in the system are reference units, which reduce indication errors that would occur if the dielectric constant of the fuel changes from its normal value, which is about twice that of air, and directly proportional to its density. Reference units are located on the lower end of a tank unit, and are always totally submerged in the unusable fuel that remains in the tank. The circuit is compensated for changes in temperature, and will indicate the mass of the fuel in the tanks. Fuel gauging systems can incorporate an additional indicator known as the fuel totalizer, which can indicate the sum of all of the tank quantities. In the event of a gauge failure, the fuel gauging system will fail safe and drive the needle of the failed indicator slowly to the 0 position. A test circuit is incorporated, which will simulate gauge failure. Place your cursor over the test button to activate the test. When the test switch is released, the pointer should return to its original position. If water is present in the fuel, it can cause errors in the indicating system. If the percentage of water is very large, the capacitors in the sensing units can be effectively shorted out. If this happens, the indicator needle will be driven beyond full scale. As well as the quantity of fuel measured, the instantaneous fuel flow can be shown. To obtain the indication of total fuel used, the instantaneous fuel flow must be integrated. The fuel flow meter can display either volume flow or mass flow. To indicate mass flow, the meter must be compensated for the density of the fuel. A fuel pressure gauge can be adapted to be used as a simple flow meter. This system is used on many light piston engine injection systems. Most gas turbine engines use an electrical sensor, which utilizes the change in either the torque output or the rotational speed of an impeller situated in the high-pressure fuel line to the fuel spray nozzles. This type of fuel flow meter consists of a cylindrical light alloy casting, within which are guide vanes that support the shaft of a helical vane impeller. The impeller has a magnet embedded in it. Electrical pick-off coils are situated in the wall of the cylinder casting. When the fuel flow rotates the impeller, a sinusoidal signal is induced in the pick-off coils. The frequency of the sinusoidal signal is proportional to the speed of the rotor, which in turn is proportional to the rate of flow. The total consumption is obtained by integrating the rate of fuel consumption over time. A flow meter that displays fuel consumed as well as fuel flow is called an integrated flow meter. Modern aircraft employ remote indicating systems that can be powered by either direct current or alternating current supplies. Whatever the power source, each data transmission system employs a remotely positioned transmitter located at the source of the information, and a receiver which responds to the information received. The DESIN transmission system is a simple transmission system with low torque characteristics, which is used for the remote indication of angular position. It's often used where a simple pointer and scale is adequate, for example, remote indication of flap, rudder and elevator positions, or to repeat the reading of an instrument at a remote point. The accuracy of the system is approximately plus or minus 2%. The transmitter consists of a continuous resistance ring or potentiometer, which has three fixed tappings, A, B and C, spaced 120 degrees apart, which are connected to the receiver. The input shaft carries two diametrically opposed spring-loaded sliding contacts, or wipers, which are in contact with the potentiometer. The wipers are fed via slip rings and brushes with direct current. The receiver consists of three high-resistance coils, whose axes are spaced 120 degrees apart, with a permanent magnet rotor pivoted at their center carrying a pointer shaft. The three coils are connected to the tapping points A, B and C in the transmitter. When direct current is applied to the transmitter wipers, the voltages at the tapping points A, B and C produce a current flow in the three stators of the receiver, and the resultant magnetic field is produced. The rotor magnet aligns itself with this magnetic field. The magnitude and polarity of each tapping point voltage varies according to the position of the wipers, and thus, if the input shaft is rotated, the change of voltages at A, B and C produces a variation in the current flowing in the stator coils, and rotation of the resultant magnetic field in sympathy with the rotation of the input shaft. The rotor magnet remains aligned with this field at all times, and so rotates in synchronism with the input shaft. Here the voltage distribution around the potentiometer is such that point A is at plus 24 volts, while points B and C are both at plus 8 volts. Because the voltage at A differs from that at B and C by the same amount, current flows from A through coil A in the receiver, then divides equally at the star point, with half the total current flowing through coil B and half through coil C back to the transmitter. The resultant magnetic field in the receiver, with which the rotor magnet aligns itself, is compounded from the vectors representing the individual fields. If the input shaft is rotated through 120 degrees in a clockwise direction, as shown here, the voltage distribution around the potentiometer is such that the current flows from B through coil B in the receiver, then divides equally to flow through coils A and C back to the transmitter. The vectors show that the resultant magnetic field also rotates through 120 degrees clockwise, and the rotor shaft aligns itself along this new axis.